receive answers. Okay? So as promised today, yeah. There is no session ID. We won't be doing session IDs because you could be at home in your bed doing that. Wouldn't that be awesome? Not an option. As promised, we're going to start with a couple clicker questions related to questions on the pre-assessment that very few people got correct. So either you get them right because you'll all be discussing them, which is great. I mean, I want you to learn, so absolutely, have a discussion with your neighbors. But if we still are getting them wrong, I want to make sure that we can get questions like this right. That's the bottom line, right? So I'm about to hit play, and we'll get going here. Just ignore that box that comes up. Just feel lucky that I'm getting this to work.
All right, so -3, so it's going to go by SM1, which means there's going to be a carbocation intermediate, right? So I think it's B.
Yeah, we're not at the point that I can get a countdown out there. It can be a presentation, so I'll give you about a minute or two. I'll always keep you strong and here for you. Yeah, it's never going to be like, wham, we're done. Let's try about a minute left to try and get the answer to this question. Just 1 minute on the clock. Yes.
Can't really. I might have to if it's wrong, first we have to let me know. No, yeah. Okay, so definitely go this way.
Alright, we're going to go with about 20 seconds here. I'll count down the last 5.
We'll go here.
So I'll judge by what I think 20 seconds is. It might not be a real 20 seconds. Anyone hear that NPR piece where as the older you get, you can't judge what a minute is? Do you ever see this? Very interesting. We should all try that one day. 5, 4, 3, 2, 1, and I am going to close polling now. All right. So I find it very interesting that no one wants to choose B, the right answer. It kills me. It kills me. It just kills me. Okay. So the conjugate form of this, right, is going to be the oxygen of the carbonyl protonated, right? And it's going to lead you with the oxygen of the carbonyl protonated and HSO4 minus. So the strategy to solve a problem like that is to say, let me estimate or guess or have a knowledge of what the pKa's are of each acid, right? The one on the left and then the conjugate form on the right. Now, the acid on the left here has a pK of about -3-ish, right? And this is actually about -5 to -6. The bottom line is when the pK units are within 2 units, what happens?
It's reversible.
Equilibrium. Okay? Almost all of these carbonyl reactions, so this is going to be very important to you because as you do mechanisms, you're going to have to write the correct reaction arrow. That's an expectation this term. We actually add another level to the mechanism writing, and that is to know if a reaction sits to the right, sits to the left, or is at equilibrium. And almost all of these reactions here are equilibria reactions. Okay? So, to note, that will be true as we continue through the rest of the semester. Okay, how about this question that is also causing us some trouble? What is the product of the reaction shown? Product of the reaction shown. I'll give you about 2 minutes to answer that question, minute and a half. Can't really use that much time, remember, so let's go with a minute and a half as I judge a minute and a half, which might very well be 3 minutes, I don't know. Okay, let's try for about 20 seconds. Take a guess, take a guess. All right, so go with 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and we're about to close polling. All right, we're all over the map here. The right answer is C. So 37% of you C. Okay, so this is an E2 reaction. At a tertiary center, any charged nucleophile is going to run E2. Remember, E2 is really the best competitor, the strongest competitor of all of them, SN1, SN2, E1, E2. Tertiary center, charged nucleophile running an E2 reaction. So then the question becomes, this is sort of a dual-natured question, if it's going to run E2, which of these products is it going to give me, C or D? You need to remember that the hydrogen at the beta site needs to be anti to the leaving group, which means I cannot, in any E2 reaction, pull a hydrogen from this more substituted beta center. I can't do it because there is no hydrogen that's anti to it, okay? That is the requirement, so I have to pull the hydrogen from the beta center on the other side, which means over here, and when I pull from over here, it leads me to product C, okay? So this is a dual sort of natured question. A lot of us aren't still recognizing that a tertiary center with a charged nucleophile is going to give E2. That's number one, okay? And number two is to remember that an E2 reaction requires an anti-beta hydrogen, okay? An anti either is anti in a conformational analysis way as rotation, free rotation of a single bond, or easier on rings, right? Because anti would mean the opposite symbolism to what the leaving group is in, okay? So please consider these your pre-assessments. I'll answer your question after class. The pre-assessments will be picked up on our way back. You'll get an actual sheet that tells you what you answered, and I think in parentheses it tells you what the right answer was. I'm pretty sure, the sheets that you get back. I'm not holding out on the right answers. I'll have them up in my office if need be, but you're welcome to come in anytime and look at the pre-assessment and compare, try and figure out what you did wrong and have conversations about it. But the pre-assessments never leave my office. So if you want to look at your pre-assessment, the actual questions, you need to actually come into my office with your answer sheet and sit down and look at the pre-assessment there. Okay, I remind you that I have open office hours from 9 to 3, Tuesdays and Thursdays, and you generally can find me back in my office for a few hours, Monday, Wednesday, Friday after class. Okay? All right, so last class, Friday, and I did actually forget to say Happy Valentine's Day. So Happy Valentine's Day. I should have led with that on Friday, so sorry about that. We were talking about MO theory, okay? And for those of you that were online, you actually saw how crazy my house is. I tell you, on Friday, the cleaning people came, for the love of God, I don't know how they got in, because we weren't plowed out. Our entire neighborhood wasn't plowed out, right? But the cleaning ladies come trudging in with their vacuum cleaners, and I'm like, you have got to be kidding me. So they're vacuuming the upstairs. We're all in the basement in one room while I was teaching that class. So, you saw that I don't know how to turn my microphone off and maybe just my volume, so that was entertaining. It's only gotten worse, and I have to say that I'm so happy to be at work today, but my husband, the poor soul, is at home because he has the day off with 2 kids. Good luck to him. So, in the meantime, though, we were talking about MO theory. We talked about a very simplistic system, a conjugated system that has 2 pi bonds in conjugation. Today, I thought we would bring in 3 pi bonds in conjugation and just sort of one-up it and talk about those principles in review, okay? So today we'll be talking, the simplest 3 pi bonds in conjugation, right, is 1,3,5 hexatriene. That's what this is, 1,3,5 hexatriene. But it's 3 pi bonds in conjugation. I can see that because it has the pattern double, single, double, single, double, right? So whenever you have double, single, that's conjugated pi bonds. So these are now, in essence, 6 carbon atoms that overlap, and 6 pi electrons are being shared to some extent. How much sharing is going on can be depicted from the molecular orbital pictures that we can draw. But there are 6 pi electrons that are being shared in this conjugated system. Remember, I answered the question of how many pi electrons there are in the conjugated system by simply counting the number of double bonds. For each double bond, I have 2 pi electrons. So in total, the system has 6 pi electrons that are being shared. Now those molecular orbital pictures, of which we had very systematic ways of drawing them, they actually describe to us how those electrons are indeed shared, right? So there's what we would call bonding interactions and anti-bonding interactions, and that's simplistically what we were looking at. Now I can draw, relatively quickly, 6 molecular orbitals. 6 molecular orbital pictures is what would be expected because you have 6 p orbitals, 1, 2, 3, 4, 5, 6 p orbitals that are going to come into form my pi molecular orbital system, because each of those carbon atoms is going to maintain 1 electron in its unhybridized p orbital. That's what we would say if we were talking about VSEPR theory. But in molecular orbital theory, we would say there's 1 electron in each of these p orbitals that's going to metamorph, right? It's going to change into this pi molecular orbital system, okay? So there are 6 that I can draw. How many of them are going to be bonding molecular orbitals? 3, because half of them will be bonding and half of them will be anti-bonding. Okay, so the question on the table here right now is how quickly, and I'll give you a minute to do this, and I'd give you more time if we had more time. If it was, I met you every day, we would certainly do these activities more. Give you a minute to see if you can draw the HOMO and LUMO for this system. Can you draw the HOMO orbital picture and the LUMO orbital picture for this system? So here are some guidelines that I'm drawing on the board as you're working through it. We said the easiest one, right, is psi 1. The lowest energy orbital system would be full overlap of all the p orbitals, right? And that's generally a good starting point. You can use that as a reference point as you draw the others. That first orbital system would have no nodes, right? A node would be an anti-bonding interaction. That would be against a bond being able to form between the 2 p orbitals that are out of phase with one another. Okay? This is also a symmetric system. Now, we said systematically that as I jump to the next highest level orbital, I'm going to flip between symmetric, asymmetric, back to symmetric, back to asymmetric, etc. And every time I jump up one energy level, I'm going to include another node. Okay? So as we come through to do this, my HOMO picture will look something like this. Look something 1, 2, 3, 4, 5, 6, something like this, okay, where there are 3 bonding interactions, right? 1 bonding interaction, because these p orbitals are in phase, right? 1 bonding interaction, a 2nd bonding interaction, a 3rd bonding interaction, because these now are the ones that are in phase, but this is what I would consider an anti-bonding interaction in here. So here is one node present in my system, and here is the second node present in my system. Okay? I know they're a node because as I move from this orbital to its direct neighbor, I have unshaded, shaded, which means the phase changes. Okay? And that's a sign of an antibond, or the inability for those lobes to overlay or to share, and hence that would be considered an antibond and a node, because a node says it's a point in space where there's zero probability of finding electron density. Okay? Does everyone see how I got this? And HOMO stands for?
Highest occupied molecular orbital.
That's very good. Okay, close enough. Highest occupied molecular orbital. Highest occupied molecular orbital. It's occupied because if I have 6 pi electrons to fit, 2 of them are going to go into my most stable, 2 are going to go into psi 2, and the remaining 2 of 6 are going to belong in this HOMO, right? So it's the highest occupied, meaning there are electrons in my orbital system for this pi MO system, okay? LUMO is lowest unoccupied, right? LUMO is lowest unoccupied, and so one depiction of this is something like this. Now there are 3 nodes, and it's asymmetric, and it's the lowest unoccupied molecular orbital system. Now, on an exam, there is a small level question that would ask you questions about molecular orbital theory. It will be tested to some extent, your ability to, generally it's a recognition, recognize diagrams, being able to order them, maybe psi 1, psi 2, psi 3, psi 4, or identify a HOMO orbital for a given system shown, or a LUMO orbital for a given system shown. It's generally a recognition, though, and not a straight draw from scratch. Okay, that's generally the types of questions that you see. Okay, you should understand a bonding interaction and anti-bonding interaction. That certainly is important. Okay, now the one that we did in class, or in, well, I guess in class, the online class, was for 1,3-butadiene, right? 1,3-butadiene. And we said, you know, we were going to draw these beautiful HOMO-LUMO pictures for 1,3-butadiene. The question I pose, though, is do you think this gap, this energy gap here, this delta E, which is the HOMO-LUMO gap, do we think that's smaller or larger than the system we talked about in class on Friday? What did we say? Smaller. As you increase the conjugation, as the conjugation increases, I have 2 double bonds in conjugation in Friday's lecture, 1,3-butadiene, the molecule on the bottom. I've increased the conjugation for the molecule we're talking about in class, because I have 3 double bonds in conjugation, okay? As I increase the conjugation, you actually see a smaller delta E. So the wavelength that shows the maximum absorbance is, I think it's roughly 220, roughly 220 nanometers for 1,3-butadiene, and it's actually roughly 260 nanometers for 1,3,5-hexatriene. So we do have evidence that the delta E, the gap, the HOMO-LUMO gap, is actually closing as we increase the conjugation. And I said to you that as you increase it more, and you can go look up all these lovely pictures of dyes, etc., you'd find that we start absorbing in the visible range, right? Which is why you have a beautiful yellow-colored shirt and a red-colored shirt and this beautiful blue, right? Yeah, I'm absent of color. I realized that today. So in this case, this is what we talked about. And the last piece of what we talked about was to use Beer's law, okay? Beer's law, right? Technically, it's called Beer-Lampert's law, but I don't know why it's always been abbreviated. Clearly, Beer won out in that argument. But Beer's law is A equals, what we say is EBC, but E is an epsilon, right? So it's a Greek letter. It's not E as in the letter E in our American alphabet. In this case, what does this epsilon stand for? It's an absorption coefficient. We call it the molecular absorptivity value. And how do I know what it is? Like, what is it for this molecule? It'll be given. That's exactly right. So you're all going to ask that question eventually. But I'm telling you right now, it'll be given. It's different for every system. Every system has a different molecular absorptivity value at its lambda max. And that has to be a measurable entity. You actually go to experiment, you devise a whole bunch of experiments, and we derive the actual values. And they're tabulated, they're in charts, you can find them online, etc. But this has to be given to you, okay? What is B? The path length. The path length is almost always 1 centimeter. Cuvettes are generally standard 1 centimeter. The only time you use one that is really different than 1 centimeter is if you had a really expensive sample, right? Like when I did my protein work and I solved the structure using NMR spectroscopy, we had to grow using minimal media, which meant we used C13 glucose and N15 salt. And my sample was like $2,000, $3,000 for one sample to get like 15 mgs of protein. That's it, 15 milligrams, which is nothing, right? So that sample was precious. I was never going to use a 1 centimeter cuvette ever. I was going to use the smallest one I could find, so I would get in the least amount of trouble. And then C is concentration. So the simplistic problems are to say something like, here's an absorbance value, give me the concentration. Or if I had a sample that had a concentration of X, what would its absorbance be, right? It'll always be ratioing between absorbance and concentration, okay? We'll see some of these on the weekly quiz. This is just a very quick review of lecture from Friday. Are there questions that are still lingering about Friday's online lecture? Okay, great. So we're going to talk today about 1,2 versus 1,4 products. Okay, so we're going to start talking about the reactivity of these conjugated systems. So there are two main reactions that you're going to be held responsible for that I can think of off the top of my head. I hope that my head is still working. I had a huge sledding accident, so who knows. One of them is to add a hydrogen halide to a conjugated system. Okay? That's one reaction we're going to be talking about. That's what we're going to be talking about the remainder of today. This goes to the 1,2 versus 1,4 product. Everything we'll be talking about today. The second one is Diels-Alder. So this is the second type of reaction that we can talk about when we're talking about these conjugated systems. And this is what we're going to be lecturing on Wednesday. So the two mainstays that are in this chapter of conjugated systems before you hit aromatics. Okay, so let's start with the simplistic system to get some of the terminology out and some of the reactions out, and then we're going to sort of step it up and make sure that you can do them for more complicated systems. So for that, we'll start with 1,3-butadiene. 1,3-butadiene. So here is my simplistic system, and I'll work with HCl. This is very much like everything you know. You should already know how to start this reaction because you should be able to identify the nucleophile and the electrophile, and you should be able to run with the reaction. Okay? So I have nucleophilic attack at an electrophilic center, just like alkenes, right? And I drop off my Cl. The biggest mistake that people make with these conjugated systems is they don't create the allylic carbocations. Remember, those allylic carbocations win out almost all the time. Always create the allylic carbocations. Now that's obvious here, because the system doesn't lend itself to something you would even consider more stable. But you'll see as we run out the system how that can really become a problem. So in this case, the hydrogen will add to the tail end, leaving behind the allylic carbocation. Now this allylic carbocation has resonance. All resonance needs to be drawn on an exam in mechanisms. When you're asked for a mechanism, you are to show all of its resonance structures while you start getting -2, -2, -2 for no reason, because you should be able to draw the resonance structures. So in this case, the resonance structure is this one here, and this resonance structure lends itself to formation of this potential carbocation. Okay? So there are two carbocations that can form, and one of them is more stable, carbocation-wise, intermediate-wise, one of them is more stable. Which one? The top one or the bottom one? Top one. Okay. So if I were to use my reaction coordinate diagram language here, right, and I were to put on just what I know, we always have to put the starting material somewhere, so I'm just going to randomly start it here. My intermediates I know are less stable than my starting material, less stable than my products as well, but I have two potential intermediates, one that's less stable and one that's more stable. So we will call one of them A, just so we can keep our reaction coordinate diagram neat, and one of them B. So here is intermediate A, here's intermediate B, okay? And I just put in here diagrammatically what you just expressed to me. That A is secondary allylic and more stable than B, which is primary allylic. So on carbocation stability alone, you note that B is more stable, okay? As you come through, each of these intermediates could potentially be captured and to form product. Now, hopefully you remember that there are two potential products that can form from the top reaction. I can get both R and S stereochemistry here. That would be a mixture, it would be a racemate, right? Because I went through a carbocation center. And my bottom reaction is only going to have one potential product because the center that was attacked by Cl- doesn't become a stereocenter, an asymmetric carbon. So it doesn't matter if attack happens from the front or the back. There's no distinguishment between those two products. So this is what I get from the bottom reaction. So there's three potential products. Yes?
Would you want us to draw the bottom reaction on an exam? Or
Okay, this is the great question. Okay, the answer actually is a little bit more complicated. Okay, so let's consider these products themselves. Now, negating everything that's occurred before, let's look just at the products. Which of these products is more stable? The one that's come through path A or the one that's come through path B? The products themselves, B. And why is B more stable? Because the double bond is more substituted, right? The double bond is di-substituted here. It has a methyl group on one side and a chlorinated methyl group on the other. Whereas in the top products, I only have one substitution, right? It's chlorinated ethyl group, one non-hydrogen substituent. So definitely B is more stable. So as I come out here, B is more stable than A, for sure, right? See how they've crossed themselves, okay? Now, the question is we're going to have to fill this in, and we're going to come back and talk about these reactions. We need to fill them in with our free energy of activation as we come toward the intermediate, leading to our free energy of activation coming toward our product. So the question I pose is, which one of these, path A or path B, is going to have a higher free energy of activation? A or B? B. And why is that? There's some famous guy who had some great postulate. Hammond's postulate. Great. And Hammond's postulate speaks to us, right, and says that we're going to have a larger free energy of activation leading to the less stable product because it has a high carbocation flavor at the transition state. So you can go review that. So for sure, we're going to see a higher free energy of activation coming through step to intermediate B here. And as they come out the other end, there's really no difference in the two in terms of energy of activation, nor does it matter what it is, actually. That doesn't even matter in this case, because we are always going to see,
Yeah.
is that what you're saying to me? Yes, I just saw that. The minute the hands go up, I know something happened. Thank you very much. Nor does it matter because we can only ever measure the rate determining step, the slowest step. So really that's step one. So we don't really have a lot of information on step two anyway, okay? So there's obviously a crossing of the guard. And there is a way that I could generate either or product. I can generate either those from reaction A or those from reaction B, depending on how I ran my reaction, okay? If I run my reaction at low temperature, this is what I'm going to get. This is a reaction run at low temperature. That is because this reaction will not have enough energy in the system to create the most stable product. That's in essence what it means to run at low temperature. It means I don't have a lot of energy in the system, and I have to follow the lowest energy path from start to finish. Okay? I must follow the lowest energy path from start to finish. To get set B here, I can run these reactions at a higher temperature, and a higher temperature is going to leave enough energy in the system to actually choose to come through to form the more stable product. Okay? Now that is not necessarily the most, doesn't come to you so easily. And really the principle at work here is called microscopic reversibility. It is always at play with every reaction that you study. Even the most exothermic reaction does have the propensity to come back toward the reactants and try again. Okay? So if there's enough energy in the system, if anything happens to come down to A, and microscopic reversibility pushes us backwards, probability-wise, we can lend ourselves to B when there's energy to follow over the higher free energy of activation path. What is so amazing about these reactions is this. I can run these reactions at low temperature, this very reaction at low temperature, and I can collect a product. And I'm on ice, and I collect my product, and it's so cool, right? And I can study it. I see by NMR that this is exactly the product that I have. I can take my product off ice, and I can leave it out at room temperature. Hour, 2 hours, depends on the system. And I can go back and check. And you know what's actually happened? I've actually moved to product B. It is absolutely amazing how this happens. So if you keep your reaction mixture intact, you can actually change the outcome of the reaction. It's amazing. So running at low temperature means that we call this product specifically a kinetic product. Because a kinetic product is one that's going to be garnered when there is no heat energy in the system, and I must be following all kinetic principles. Kinetic principles are to follow the lowest energy path from start to finish. Okay? When I run these reactions at high temperature, we call this the thermodynamic product. The thermodynamic product. And the thermodynamic product, in essence, implies that there is heat in the system to choose the lowest energy product in the end. Okay? Now, this is one labeling of these products. There's a second labeling of these products that now throws a whole wrench into these reactions. So just follow with me systematically how this is done. I know for a fact, because we thought through this whole reaction, we thought through it all, right? So I know what my kinetic and thermodynamic products are. The question is, it becomes, which one is my 1,2 product and which one is my 1,4 product? Because that's the other labeling for these types of reactions. One labeling is thermodynamic and kinetic. And the second labeling that you're responsible for is a 1,2 product versus a 1,4 product. Okay? So the question is, how do we number these systems? We number these systems for carbon 1 being the carbon where the electrophile added. Okay? So that's garnered right here. This is 1, right? The electrophile adds to the non-allylic site, I guess would be one way to say it, the non-allylic site, and I call that automatically carbon 1. That's where the numbering starts. Okay? That's the requirement, that's the systematic methodology. Number carbon 1 where the electrophile adds. Okay? And now I number my carbon backbone through the remaining pi bond. Through the remaining pi bond, which means I need to number right to left here, right? 2, 3, 4. Okay? So carbon 1 is always the carbon where the electrophile added, and I must number my system through the remaining pi bond. Okay? And now I read out in my products, where did the electrophile add? That will always be carbon 1, right? And then where did the nucleophile add? To form the kinetic product, here in our example, this example, to form the kinetic product, where did my nucleophile add? Carbon 2, 3, or 4? 2. So this is also called my 1,2 product. Okay? 1,2 product comes from a systematic methodology of numbering your carbocation intermediates. Your labeling of kinetic product came from what? stability of not of my product. Kinetic product came from my stability of the intermediate. Okay? So this is a given. 1, 2 is systematic, right? You barely need to do any thinking with that, right? Because you can memorize that number 1 carbon is where the electrophile adds, and I number through the remaining double bond. It's going to be easy for me to identify. The kinetic product requires thinking. It requires me to recognize that this is the more stable carbocation intermediate in the course of the reaction. So my thermodynamic product has an alternate name here. And what is the thermodynamic product also called in this reaction? 1,4. 1,4. That's exactly right. Because I have now my electrophile adding at carbon 1 and my nucleophile adding at carbon 4 in my numbered system. Okay? Does everyone see this? All right, so this begs the question, what is low temperature and what is high temperature, right? I mean, that begs the question because we don't ever really write low temperature or high temperature. We generally write reaction conditions. I'll get you in just a second. Let me just answer this last question. So the low temperature conditions that we are always going to assume on any exam, okay, is going to be a dry ice acetone bath. Dry ice acetone bath is one of the coldest maintainable temperatures. This would be minus 78 degrees Celsius. So we're going to go with that for low temperature. That is being completely black or white. There's no gray there, right? Because low temperature really depends on the system. Sometimes it's 0, sometimes it's minus 20, and sometimes it truthfully is minus 80, right? So high temperature will be indicated to you by saying room temperature, okay? This is how we will communicate with you, the exam takers, homework answerers, right? What we mean when we're talking about generating a kinetic product or a thermodynamic product. Okay, yeah.
For room temperature, would they also say something like 22 degrees Celsius?
Yeah, I mean, yeah, sure. Yeah.
I was just wondering, what would happen if your electrophile was added somewhere in the middle of a compound? Like, how would you count 1, 2,
I
3,
would
4?
still count it as carbon 1 and number through the pi bond. That will always systematically work. Okay?
And if it's in a symmetric molecule?
Okay, we're going to do a harder example. I think this is probably going to clear up any other questions. Are there any remaining questions from the simple example we have on the board? Okay, let's try one up then. Ready? All right.
It's like,
All right, you go. 2 minutes.
it just means that it's not
I want to
super
see a reaction mechanism with HBr. I'll fix that up in just a second here. So I want to see a reaction mechanism with HBr. And I want to see both labelings of the kinetic and thermodynamic product as well as the labelings 1, 2, and 1, 4. yourself is, which double bonds are you going to use to react? Which double bond? Some people use the left one, which I've indicated with Roman numeral 1 here. We can use the one that's Roman numeral 2. You guys, this is a question that I asked my 231 class and get you guys comfortable with. Is it a question that's been asked to you? Would you know which double bond reacts faster?
One plus substitution.
Okay, how many people would say 1? How many people would say 2? Okay, very good. You're not all voting still though, I can see that, and I'm only, I'm not a computer up here. Let's try again. How many vote for 1? Okay, yeah, okay, we can play this game all day. Unreal. Can't own up. The answer is 2, okay? This one labeled 2 will react faster, and that comes from the types of intermediates that form, okay? Simplistically, without considering allylics, okay, the left double bond can form a primary and a secondary carbocation, where the double bond on the right can form a secondary and a tertiary. Those intermediates, creating a secondary and a tertiary carbocation intermediate, will form faster than the comparative, right? So, while I might get higher regioselectivity by double bond 1 reacting, double bond 2 reacts much faster because it forms more stable intermediates. So, we won't show, so it's the first discerning thing that we have to do is decide mechanistically which double bond is going to react. Yeah?
Does that mean the first double bond doesn't react at all?
That's exactly right. That when I add 1 mole, because in essence we're only showing the addition of 1 mole here, when I add 1 mole of HBr, double bond 1 is not reacting at all. It's only 2 that's going to run my initial reactions. So, okay. So now we run with double bond 2, and the question is, which intermediate do you form? The intermediate that you form should be this intermediate only. Now, how many of you didn't do that, right? Because this is the next trick as we one-up the questions, as we layer on, the old material. This is comparing a tertiary to a secondary allylic, right? If I think about what the 2 are just from that double bond reacting, I can get a tertiary versus a secondary allylic. And secondary allylic is more stable than tertiary. Secondary allylic carbocations are more stable than tertiary. So, therein lies the second problem. So we aren't going to form any tertiary. So I said when we went through the first one that we're always going to form the allylic carbocations. Always the allylic carbocations. So this guy is out. Does everyone understand what I mean? The secondary allylic's more stable. Yeah.
It doesn't form at all, not even in like
Doesn't even form at all. Isn't that crazy? Yep.
That was my question.
Okay, great. So in this case then, we have secondary allylic as our first carbocation intermediate, and this is going to be labeled as carbon 2, because the electrophile then added over here, right? So I'm just numbering my intermediate as I taught you. The electrophile adds to carbon 1. The electrophile added to that tertiary slot to make the secondary allylic then carbon 2, and carbon 3 and 4 are still in the double bond down here. Okay? So this is one potential product. I can come through and show 2 potential stereochemistries of that product. This is one, and this is the other. Stereochemistries, 50-50 racemate, right? But these are them that I get out of the reaction. Is this reaction, though, thinking the kinetic product or the thermodynamic product? It is the kinetic product. That's exactly right. This is the kinetic product. Okay? The kinetic product. I know it's the kinetic product because I very quickly go back and draw my other resonance form of this intermediate, and I see that I can have a secondary allylic. That's what I started with. And when I do my resonance structure, I wind up with a primary allylic. The primary allylic is less stable, and my kinetic product is identified through the most stable carbocation. My initial carbocation I drew was more stable, so as I follow through, this is going to lead to my kinetic product. And my kinetic product is at the 1,2 or 1,4? 1,2. Okay, great. And this is then gonna lead to my thermodynamic product, right? As I follow through here, I'll get one potential product out of this reaction, and this would be labeled as my thermodynamic product, and also my 1,4 product. Okay, so you guys are probably identifying a pattern here. Y'all like pattern recognition. What's the pattern you've identified? The kinetic product is the 1,2 product. Okay, I'm about to throw a wrench into that pattern. Here we go. What do I get from this reaction?
Can you just a double bond there? Or no?
This is actually a two-step synthesis. It's two reactions that have been put together. This is the starting material. Let's see if we can't draw what the product is after step 1 and use that for step 2 to garner what the product is of my two-step synthetic scheme. Okay? So as I think through the problem and we think out loud, the first thing to do is to recognize the symmetry in the system, right? So recognize it doesn't matter which double bond I react. That's nice. So I don't have to do that piece. So now I'm going to react either double bond to always give me my allylic carbocation. There is my allylic carbocation, right? That's my allylic carbocation. I've used one double bond and I've made the allylic carbocation. Okay, so now I have to judge, right, which one is going to lead to, by low temp, and I probably should have put in -70, we're going to cross that out. Cross that out of your notes and say, no, -78 degrees Celsius, just so we're clear. I need to think about my kinetic product. So the question is this it? Because this is the 1,2 product. If I directly attack here, this would lead to the 1,2 product. You should all agree with that. But that's not the kinetic product, okay? The kinetic product comes from the resonance form. As I think about what the resonance structure is, this is the resonance structure of that material, and this here is the more stable carbocation, therefore leading to the kinetic product. The more stable carbocation always leads to the kinetic product. This means that in this example, it's the 1,4 product that's the kinetic product. So you all identify that pattern, but you have to be very careful. 1,2 and 1,4 is systematic. Thermo and kinetic is thoughtful. It requires you to put your thinking cap on, okay? Don't fall for it. So this is the intermediate. So if I do after step 1 then, I can say that I have this as my, I use HBr, material, okay? This is the product of step 1, okay? And as I move through to step 2, which is the addition of HCl, I only have one remaining. What do we think the product is from that reaction, the major product? Think through that, we can get this carbocation or this carbocation. Which carbocation is more stable, do you think? The top or the bottom?
Top.
What does this Br do?
Cool.
Pulls electron density. Which one's it going to be more disastrous for? The top or the bottom? The top. This is bad. This is definitely less stable. This guy pulls electron density. It's on a neighboring carbon. It's going to pull electron density toward it. It's going to make that positive charge even more positive, even less stable, right? Not good. So we have this here, but what is this going to do?
Rearrange.
It's going to do a hydride shift. So I have a hydride shift. that leads to now this, and then finally to the product, which